Okay, now let's see how we can use linear approximation to approximate the natural log of 1.2. So the idea is we want to think about this somehow in terms of either a tangent line or differentials. Well, if you want to approximate natural log of 1.2, what we have to do is figure out what kind of function we should use and then where we should find the tangent line. Well, there's kind of an obvious function here. We're taking natural log of something. So let's try f of x equals ln of x. Now, how do we find an a value that is appropriate? Well, we want an a value that is close to 1.2, because the whole point of a linear approximation is that it works pretty well if the x value, or the input that you're looking at, like 1.2, is close to wherever you found the tangent line. So a should be close to 1.2, and we want ln of a to be easy. Right? For example, if you pick a equals 1.1, that's certainly close to 1.2. But if you don't know what natural log of 1.1 is, that kind of doesn't help you. Well, there's one really easy input for natural log that happens to be pretty close to 1.2, and that's a equals 1. Because remember that the natural log of 1 is equal to 0. So we're going to use this function and this a value. And I'm going to illustrate how you can solve this in two different ways. First, let me do it using differentials. So we'll say y is equal to the natural log of x. And that means that dy is 1 over x dx. Remember the derivative of ln of x is 1 over x. And so the idea is that x is going from 1, that's the sort of original a value, up to 1.2, and we want to know how y changes. Y goes from 0 to something. Since x goes from 1 to 1.2, that means delta x, or dx, is 0.2. So that's our dx. Y is going to go from 0 to something, so that means that delta y will be whatever that something is minus 0. And we can approximate that change by dy. Well, we have that we're starting at an x value of 1, so we plug 1 in for x. We'll plug 0.2 in for dx. And so, in fact, it turns out in this case that dy is also 0.2. So what that means is this, that ln of 1.2 is approximately equal to ln of 1 plus the change in y, which we're approximating with dy. And so in this case, we get a value of 0.2. Now let me show you how that looks if you prefer to think about it in terms of tangent lines. And maybe it will even help to draw a bit of a picture here. So here's the graph of y equals ln of x. It crosses right here at x equals 1, and that's in fact where we found our tangent line. So the point is the point 1, 0. And the slope is what we get by plugging 1 into the derivative. Well, the derivative is 1 over x, and plugging 1 in gets you 1. And so the equation of that line is y equals 1 times x minus 1 plus 0. So, in other words, y equals x minus 1. And so finally we say, well, the natural log of 1.2, I mean, that's what you would think of as being f of 1.2. And since 1.2 is pretty close to 1, the height of that point on the curve ln of x should be pretty close to the height on this linearization that we've found. So L of 1.2. Again, L of x is what I'm calling this tangent line. So L of x is just the function x minus 1. And so again, we get that natural log of 1.2 is approximately equal to 0.2.